Next speaker is a friend and also is a committee member of our compound semiconductor committee in SEMICON Taiwan, Mr.Stephen Coates. And he's currently the managing GM of Asia region and also the VP Global Operation for GaN System Corporation. And his past experience also including the Digilens, Burns Electronic, and or in executive level. So let's welcome Stephen.
So thank you, Barry, for such a great introduction. And really, it's a great honor for me to be here today, seeing so many new friends, meeting new friends, and seeing so many old friends. And I'd really like to take a moment to say thank you to SEMI, Taiwan. Thank you to the Power and Compound Semiconductor Committee, which, as Barry said, I'm fortunate to be a founding member. And then lastly, thank you so much to鴻海for being such an excellent sponsor and advocate for wide bandgap and compound. I think I've actually been in almost all of the sessions from when we started here. And I think the growth that we've seen, I think, just underlines how important wide bandgap is becoming. So today, I'll share with you some thoughts. How GaN's reached its tipping point, how GaN systems is transforming the world, and how in the transformation, we're really seeing smaller, more efficient, and more reliable and highly cost-effective power electronics. Our industry is poised at the beginning of what may well be the most significant revolution in electric power since electricity was first used in a few blocks of New York City over 150 years ago. Global electricity demand has grown by almost 33% over the past decade, and it will continue to grow 50% more by 2050. So at the same time, renewable energy accounts for almost half of global power generation, and power and power electronics really are at the center of our world. Here are the three mega trends that are really driving the revolution in today's power electronics. So first mega trend, the panel on the left, the digital economy. The world's turned more digital. Digital equals data. Data crunching, data storage, data transmission all require more power. And this growth of data is resulting in significant needs for data centers and in 5G. And the infrastructure requirements really require highly efficient and smaller sized power electronics. Secondly, the middle panel, electrification. Many devices that weren't electric before are now being electrified. Best illustrated by the center picture, the electric vehicle. Many, many other examples. IoT, another example where we're putting sensors, effectively everywhere. Sensors need power, security cameras, cell phones, many, many other examples. This drive for electrification is really driving the need for efficient power electronics. And thirdly, on the right, energy efficiency. So here, CO2 reduction, energy efficiency, driving clean energy. Gary, thank you so much for an excellent speech. I think you will hear some of the messages you were delivering also being delivered by me, and I suspect by many, if not all, of the very eminent speakers that we have here today. So the need for power electronics that uses less energy and less materials is absolutely incumbent, I think, upon us all in this room as we think about how we chart out getting the job done. So let's take a moment to think about the major contributors and activities in our digital economy today. So take a look at the world in numbers. In 2021, more than 10 billion active IoT devices being used, connecting 127 devices to the internet for the first time every second. And in 2025, we can predict over 150,000 IoT devices connecting to the internet every minute. So the amount of data generated by IoT devices is over 70 zettabytes in 3 years' time. And just for reference, 1 zettabyte equals 1 trillion gigabytes. So we're talking big data here. And artificial intelligence, it's everywhere. So applications, algorithms, all used in many areas to transform the way that we live and the way that we work and, frankly, the way that we play and that we relax. Note the insight from Sanjay. Many of these applications require 6 times more power, 6 times more DRAM, 6 times more memory. And all of these, as you will see in some later slides, you'll see that the application of GaN delivers smaller power electronics, higher efficiency, and then you can see that the space that's freed up can be used for more memory. Another market segment adding to skyrocketing data is the autonomous vehicle. So some good metrics here, but kind of some highlights. The autonomous car will generate 4 terabytes of data per day. Onboard cameras, radar, LiDAR, sonar, GPS. And if only 10% of today's US drivers adopted self-driving vehicles, that'll generate 40 zettabytes of data annually. So the autonomous vehicle, another huge source of growing data. So electrification, nearly everything that we touch requires power, and the number of devices is rapidly increasing. So adding to the electrification list, of course, the electric vehicle. Volumes forecasted to grow 30 times over the next 20 years, and they're probably conservative numbers, by the way. These growth rates are more in line with consumer devices rather than cars. So this really is leading to this huge semiconductor market growth and, frankly, opportunity. And EV growth really helps reduce dependence on fossil fuels, reduces CO2 emissions, which in line helps to reduce greenhouse gases. But it increases global electricity demand by 30%. So we need to make sure our power electronics are small, lightweight, efficient, and cost-effective. So now let's just take a moment to think about how the digital economy and electrification are impacting global demand of electricity and how renewables play their part. And really, what is industry? What are we all doing to think about supporting these initiatives? So just reflecting back on that third megatrend that I mentioned, energy efficiency. I think there's some good news here. Renewable sources, climbing to upwards towards 40% of demand. So that does drive CO2 reduction. It does, supported by the regulatory requirements. And frankly, as our demand for sustainability as consumers, that's the good news. The not so good news is that it still leaves 60% of electricity that will be fossil fuel based. So let's just take a moment to look at why this is important. So unfortunately, we saw during COVID and the lockdown, many downsides to industry. One of the interesting points that we saw for the first time the kind of impact that we as humans have on the environment. So it's clear from these images that we have a challenge and we have a responsibility to make things better for us and for our future generations. To boost energy efficiency and help make the planet healthier, companies and governments are stepping in. In the data center area, governments recognize that energy, its supply and demand, is strategic to national economic and security needs. So they've set rules, targets, plans. In automotive, consumers that have been under regional government regulation for some time, they're all recognizing that electrification must be a key part of their strategy. And then thirdly, in the consumer area, we all like to get it says Amazon, but I'm going to say PC Home and Momo deliveries. Most of these trucks, though, emit CO2. And then there are all the warehouses that need to be lit. And then there are the robots to do the picking and the packing, along with the computers. All of these things demand power. Fortunately, some of the big players are taking actions into their own hands. So on the surface of it, all this data and electrification, it really looks great. But we've all got to do our part in the reduction of energy loss, our part in the reduction of material usage, and our part in the reduction of cost, or we could end up in a pretty dark and dreary place. So that's why we're here today. Talk about the mighty power transistor and its important place, its primary place in the efficiency equation. So this is a really key chart. I'm going to look at 3 panels, and I'm going to start with the panel on the left. Power electronics, truly ubiquitous, everywhere. There are power sources, there are power users, and always in the middle of those two is the power electronics, and the heart of that, frankly, is the power transistor. So this can be as simple as a phone charger, all the way through to the quite complex electronics in your electric vehicle. And then the center panel. There are universal needs for all power systems. Higher efficiency, so we don't waste the power as heat. Small size, lightweight. Lower system cost. So while the wide bandgap transistors might be a little more expensive today, we're really seeing delivery of lower price systems. And I'll show an example of that later. And then thirdly, on the right, transistors are the key to achieving the objectives, that we talked about in the middle of the slide. And many well-respected people have called the transistor the most important invention of the 20th century. And it's important enough that these inventors were awarded the Nobel Prize. So bottom line, power transistor is the most important component, the most critical aspect in the system, and therefore you really need to have the best-in-class power transistor. That's critical. So having established that the transistor's key, let's look at where silicon's taken us today. So this RSP chart shows a couple of things. It shows that silicon's reached its maximum performance in either 2D or 3D structures. And as we've discussed previously, the world's not stopping its demand for smaller, lighter, more efficient, more cost-effective power electronics. So the industry's shifting its technology. And then thirdly, GaN has already dramatically exceeded the performance of 3D silicon and, frankly, silicon carbide. So, GaN is still very, very far from its theoretical limit. So silicon, 3D silicon, GaN today, theoretical limit. 3 orders of magnitude for continual performance increases. So market requirements and GaN supplier readiness really make now the right time for GaN. So in the left of this chart, you can see how GaN, silicon carbide, and silicon compare in some of the key parameters. And as you can see on the right, what GaN delivers is 4 times higher efficiency, 4 times smaller size, and up to 20% cost saving at the system level, which is fundamental to the delivery of best-in-class products. So the transition to GaN from silicon is not a unique shift. I think we're all very familiar with the pace at which there have been advancements over the years. So why? Why is GaN at the tipping point? So really 3 points to make here. Firstly, the technology. GaN's more reliable than silicon carbide, and it's just as reliable as silicon. So the second point, driving volume. Driving volume is what is driving costs down, driving up yields, to getting to the point that the GaN transistors that I'm shipping today yield out at the same levels as silicon transistors. And then the industry megatrends. We touched on this a little earlier. So in GaN systems, we focus on 5 key market segments: consumer, automotive, data center, industrial, renewables. So focusing on automotive, where is GaN being used today? It's being used in all 8 of these applications in the electric vehicle, with the traction inverter, the DC to DC converter, and the onboard charger being the early adopters and the fastest pace use of GaN today. And then here's an example of a customer, a tier 1, European tier 1, who designed a 7.2 kilowatt onboard charger 4 different ways: silicon carbide, silicon, other GaN, and GaN systems. And as you can see, 5 times smaller size, 3 times lower losses. So GaN systems GaN is outperforming silicon and silicon carbide. So in the electric vehicle, here's another perfect example. Here's the inverter. So one of my customers publicly shown their cost breakdown. So you can see on the left of the chart here, the right-hand side of the chart, sorry, the onboard charger, a 1.7 increase in power density, the GaN inverter in the same form factor, with an 8% lower cost. And then over here on the left-hand side, you see the Toyota all-GaN car that uses GaN systems GaN in the onboard charger, the DC to DC converter, and the traction inverters. So data centers, driven to provide higher performance. We talked earlier about the numbers that are really driving the data center use. So higher performance, that leads to higher power conversion and higher power consumption. So 71% increase in CPU, 50% increase in the GPU, 28 times increase in memory, 67% increase in power consumption. So you can see that there is a requirement for higher efficiency and, frankly, smaller size power supplies. There are largely untapped solutions in hardware efficiency. In this chart, you can see 22% loss front end to back end in the silicon-based power supply, and a 10% gain to 88% using GaN. So GaN really solves 3 of the design challenges: the requirement for increased efficiency, the requirement for reduction in emissions, and the requirement for reduction in size. So with GaN, data centers have more servers and storage per rack. So this is a critical chart. You see here a GaN power supply and a silicon power supply, 1.5 times more power from the same form factor. And what that delivers in the data center is more servers and the requirement for less power supplies. And then that manifests itself, if you actually take a look at the numbers, you get a reduction in OpEx, you get a reduction in CO2, and this is per 10 rack set in the data center. And it delivers a $3 million profit by the application of the GaN power supply versus the silicon power supply. So tying it all together, in our world of more data, more electronics, the need for clean energy and the reduction of CO2, we've got to be more frugal with our materials. It is incumbent upon every single one of us in this room to be considering that. And existing legacy silicon, it has its place, but it has run out of gas. So GaN's here today, proven reliability, proven with customers, proven in the field. Now really is the time for wide bandgap. Now is the time of GaN. So I thank you very much for your time. Once again, I'm Stephen Coates. I'm General Manager of GaN Systems in Asia. My office is right down the road in Hsinchu here in Taiwan. And I'd be really happy to take a couple of questions, online or offline.
Okay, that's thanks Stephen's talk. He's always passionate about this wide bandgap material. So each time he will give you a lot of information and share a lot of stories. I love his talk and enjoy a lot. So, but time is short. We only take a couple questions too. So.
For the 1200 volt configuration, I know that currently there are people making 1200 volts GaN for vehicle electronics. And can you comment on that? And I know that people have been doing 1300 for both vehicle usage and as well as charge stations. Have you done any project in that area in particular? And my second question is, to improve the dislocation issues, people have been using MBE plus quantum dots for the interface. Have you using similar recipes for your devices? Those are my two questions.
Great questions. I'm really pleased you asked the first question. With respect to the second question, not really anything I can comment on kind of high level. But in terms of the first question, and I think, asked very well, Bob, and then also by yourself, thank you. So 1200 volt today, we have many, many customers already using our 650 volt devices in 1200 volt applications. So you may ask the question, how is that possible? Well, it uses what's known as a multi-level topology. And we've got some very unique patented topologies that already deliver the very best in class using multiple GaN transistors, effectively stacking in a cascade type arrangement to be able to deliver the best in class performance and the best efficiency at the right cost structure. So that's how 650 volt transistors are being used effectively and being designed into car electronics principally today. For the future, I think we're all working on voltage nodes above 650 volt. I think they're going to take time, but the application of GaN today fits perfectly well and delivers all the requirements using multi-level.
Sorry, the time is really short, so maybe you can continue taking all the questions during the break. Okay. And so let's thanks Stephen to give us such a nice talk today. Yep.